So first of all, since we are taping these lectures so that they can be broadcast at the Magen campus as well, for that reason, unfortunately, I've heard we can't really put on the AC, so I'm sorry if it's getting a little warm. And also, we have to be pretty quiet in the back because there's no directed microphone, so the microphone will pick up pretty much everything that is being said in the class here. So if you have anything to say, please say to me that we can discuss. But don't talk to each other, otherwise the people in the won't hear anything. Good. I think you've all gotten the email last week with the class website, right? So everybody has found that, everybody has that, I hope. There's also weekly homework problems posted there. It's all described there. There will be no more dropped classes after last week. The only one is Easter Monday, but it's free anyway. So general format of the class. Typically, we are going through, there's a couple of quite involved calculations. I will do a few of them on the board. I don't think you'll learn much if I go through each and every step. So it's always good if you just read the chapters beforehand and we can discuss and actually discuss the physics in there. We don't spend hours and hours just going through calculations from which I would usually mess up anyway. There will be two midterm exams. You can see them in the schedule. Are there any other general questions about the format of the lecture? One thing, so there's a tutor, there will be tutorial sessions, probably Thursdays or Wednesdays or Thursdays, by Michael Kreter, but he's actually on his way back from Germany. He's just done his PhD defense, so he should actually arrive today. He will arrange with you via email when we'll have these tutorial sessions, and you can also ask about the homework assignments. Homeworks are always due on, what did I say, Friday at noon, so that I have at least a day to look at them. Obviously, the tutorial sessions should be some time before, so if there's any critical questions, you can ask. And also, of course, my door is usually open. If you have any questions and you don't find Michael, please feel free just to come by and ask me. So I'm always happy to help. Good. Anything else general we should discuss? Any questions? Hello, morning. Tell me your name. Please, give me your first name. How do you spell it? Sorry. A-T-L-E. A-T-L-E. G-A-N-G. African. Thank you. Welcome. Okay, good. So then, we can jump right in. So I think of the past couple of years you have gone through the first parts of this book. I'm sure you are familiar with Maxwell's equations. If there's one thing you need to remember from the class, that's it, right? Which of course relates actual physical quantities, electric and magnetic fields, to charge and current densities. So from electrostatics already, so if we have a static situation, you've already learned that you can write an electric field in terms of a potential. So if everything is static, how did you calculate the electric field from a potential? Say a potential V, what's the relation there? You have a static electric potential, then the electric field is, somebody has to remember that. Really, nobody? There's the gradient, right? Minus gradient. The electric field is the gradient of the electric potential V. Now here one important thing. Which one is an actual physical quantity that you can measure, that you can put a definite number to? Electric fields or potential? What is the actual physical we ask, can you measure an electric field? How would you do that? It should not be just me talking. How would you measure the electric field? If you have, say, some charged object, what would happen with it in the electric field? Would exert a force. So you can measure essentially the force that is exerted on some charge. Electric field is something that you can measure. What about the potential? So voltage essentially. Can you put a definite number to here's 0 volt, here's 1 volt? Can you do that? Somebody say something, please.
You have to measure it between 2 points.
Exactly.
Usually.
Right. The potential is not a definite physical quantity. What you can measure is the potential difference, which effectively measures the gradient of the potential, measures the electric field. Right? So the potential is actually not a physical quantity. The potential is some mathematical construct that you can use to calculate a field, but it's not a physical quantity. All right, so this process is only true if everything is static. So if there's no time derivatives here, you can see that this can't really do all to it, because if you have something that changes with time, then there's something of the changing magnetic field that also comes into the electric, right? So if we go away from the static assumption, then this will no longer be true. So let's start with the magnetic field. Even if everything is time dependent, we still have that the divergence of the magnetic field is 0. And there's a very fundamental theorem about a vector field if the divergence is 0. What can you do about the magnetic field if you know that its divergence is 0? You can write it in what form? Coming back to the potential concept. If the divergence of something is 0, and prove that now, that means you can write this in terms of some kind of vector potential A and take the curl of that, right? So actually the other way around. If you write a magnetic field as the curl of some vector potential, then you guarantee that that's the divergence. Have you ever written that out? Have you ever tried that out? Or should we do that? Maybe to start out, and then just write out what this actually is. Right? So the curl of A, if we do this in x, y, z coordinates, so the curl of A, which we can write as a vector. The x component is it the A z over the y minus the A y over z. Also just to make sure everybody knows how to calculate the curl of something, right? Then we have dA x over dz minus dz over x and the A y over x minus ax over right. As this looks familiar to everybody. Now, if we have if now we take the gradient of that is the divergence of that, that's divergence B. So what we would do is do this, d over dx, d over dy, d over z, right? Okay, so we do essentially this dot product here, and then we have dA z over x y minus d2a y z dy. dx z minus 3ax. Right? And now, if I haven't messed things up here, they should all cancel out. Let's see, the az over dx dy, az dx dy, here with plus, here with minus, right? So this goes away. Dy dz dx, dy dz dx, minus plus, good. And dx dz dy, dx dy plus minus. So that means if we have some kind of vector potential A, it doesn't matter at all what this looks like, what the function is. If you take the curl of that, we can produce a magnetic field and guarantee that the divergence is zero. Okay, so that we know for our magnetic field. So the first thing, the magnetic field we can write in terms of a vector potential A. Now, let's look at the electric field. So for the electric field, we've seen things become a little more complicated now. But what we can do is maybe just put the definition in there. So we can write that's the curl of E equals, that's minus dB over dt, but dB over dt is not curl A, right? So d over dt of curl of A, right? Or we can write this as the curl of A over dt. Right? If this is mathematically well behaved, then of course you can switch these derivatives around. Okay, so what that means is that we have a curl of something on both sides. Of course, add the two things that we take the curl of. So if we take curl of E plus A t is 0. And can do essentially the same game as we've done here. If we know that the curl of something is 0, then the proof goes exactly the same way. If you have the curl of some vector field, say f or so, equals 0, that means you can write f as the gradient of some function, let's call that lambda. Then put this back in, do a similar calculation. It doesn't matter what kind of function this is. If you have some kind of scalar field, take the gradient of it, then you guarantee that the curl is 0. See, from the static case, because in the static case, curl of E was 0, so we could write the electric field as just the gradient of the potential, right? The electric potential. So now we have something else whose curl is 0. So that means, so this thing whose curl is 0 can be written as some kind of gradient of the potential. So, switching over here now. So the two representations that we've now found is that we write the magnetic field as the curl of some vector potential. And just using that, we can write the electric field as we have for the static case, minus gradient V. But now we have this the time-dependent vector potential, so we have this A term there. So this, I believe, For the magnetic field, you've already seen in magnetostatics, I think. And for the electric field, we have a correction to what we know from the static field. Just the time derivative of this vector. Okay? Good. Okay. All right. So now, let's see how we can relate, using Maxwell's equations, how we can relate these potentials somehow to charges and currents. So, we know, of course, here from first Maxwell's equation that gradient E, that divergence E is rho over epsilon naught. Divergence of E, we can just write in this form, minus the divergence of the gradient gives us the Laplace of E minus E over dt gradient of divergence. Right? That's simply Maxwell's equations there. And we can use this one to relate the potentials to the current density. So let's write curl of E. The curl of E is the curl of A, right? So that's curl of A equals, well, mu naught times current density, of course still there, and plus mu naught epsilon naught E over dt, and E we have here, right? So E over dt of gradient V, that's minus sign, right? Minus mu naught epsilon naught E2A over T. So now, if you ever worked out what's the curl of some things, effectively you do this kind of operation again on the curl as it is already. And let me make sure I don't mess up the sign here. So the curl you can actually write as the gradient of the divergence of A minus the Laplace operator. Now here's a stupid question. We have Laplace times divergence times divergence essentially. Minus, and that's in this Laplace is also divergence times divergence. Isn't that the same thing? Isn't that what here? Is it? That would be unfortunate, right? Because then just see if you look what is the Laplace operator? The Laplace is just second derivative in x plus second derivative in y, right? Plus second derivative in z, right? On A. What is this thing? So that's this thing. This thing becomes, so divergence A gives dA x over x plus dA y over y plus dA z over dz, right? And now we take the gradient of that, right? That means we have this here of the x of, let's call this n here, right? dz, z over dx, dz, and so on. Mixed terms that don't appear here. Right? So these two are definitely not the same. Right? So those are really different vector expressions. So we haven't done any nonsense here. I think. So maybe we can write this out in a somewhat more convenient form. So plug this in here. We have a gradient of this and gradient of v here, right? So we can write this both on the left-hand side. That's gradient of divergence A plus u naught epsilon naught v, right? Put this over this. And then we have minus the Laplace operator. Bring this over here, gives us minus here, u naught epsilon naught 2 over t. So now let's combine this term and this term, and on the right hand side we just have u naught j. So here we have our general ways in which we can relate charges and current densities to the potentials. So here, as for the current density, of course now you can see with everything becoming time dependent, we have these two potentials, the scalar potential and this vector potential, and they both mix in both in the charge density and in the current density. How was that in the static case, in the electrostatic case? In the static case, there was no time dependence here, so the charge density was only coupled to the scalar potential. And in the same way, the current density, since there is no time dependence here, the current density only affects the magnetic field, thereby only the vector potential. Here you can see that now suddenly the two potentials mix in with each other. Okay. Does that make sense so far? Not too enthusiastic. Any questions? Any comments? So, if not, then we can just take it from here and recall again which are the things that are actually physical quantities, which are the ones that we have freedom to adjust. Already said the scalar potential. In a static case, you can't define exactly where zero potential is. You have freedom just to adjust that. Right? You can add any number to this potential, and you still get the same thing. Right? You just add a constant. You say 0 volt is not here, but 0 volt is there. All that matters is the potential drop. In the same way, also these vector potentials are not really fixed by any physics. What we can measure is the charges and the currents and the fields E. So that means we can mess around with these potentials pretty much any way we want, as long as we don't mess up the fields. So let's see what we can do. Example. So let's start with our vector potential A here. Obviously, what we can do is just add any constant or something to it. And since we're just doing derivatives here, if we just add a constant, obviously nothing changes, right? The fields don't change. You can actually do more than just the constant. So if we say change our vector potential A to some other, say A prime, that is A plus some other vector field alpha. What do we have to require so that we don't mess up our fields? What condition do we have to place on this alpha so that it doesn't mess up the field? Once we have a negative field E, should then also be curl of A prime, right? That is curl of A. That is our field, well, that we know, that we can measure, plus now we have a term curl of alpha, right? So what condition do we have to place on alpha so that we don't mess up the field? What we want, this should be equal to the field that we have from only using A, not A prime. So this better be the same as curl of A. So that means that the curl of alpha must be 0. So in order not to change the magnetic fields, we have to require that curl of alpha is 0, right? As long as we have a function whose curl is 0, we have a huge variety of freedom of how we choose that. Right? So that means, how can we ensure that the curl is 0? In what form can we write this to make sure that the curl is 0? Same trick as we've done for the electric field there, right? If the curl of something is 0, you can write it as what? As the gradient of something, right? So that means if we write our function alpha just as the gradient of some scalar beta, then we have guaranteed, right? Okay. This same trick here again, take the curl of that, you'll find it's always 0. So if you add to your vector potential any kind of gradient of any function, you guarantee that you don't change the magnetic field. But is that all? Are we done if we simply just change our vector potential and then everything else stays?